There is a substance sitting at the bottom of the Mediterranean Sea that has grown stronger with every passing century, and modern engineers have spent decades trying to figure out how that is even possible. The Romans built harbors, aqueducts, and monuments using a concrete formula that has not cracked, crumbled, or eroded in over 2,000 years, while the concrete we pour into our highways and bridges today begins deteriorating within decades. Somewhere between the fall of the Roman Empire and the rise of modern construction, humanity lost one of the greatest engineering secrets ever discovered. And what scientists found when they finally cracked the code changed everything we thought we knew about building materials. To understand why this matters, you have to go back to a time when the Mediterranean world was in the middle of a construction revolution. Rome was expanding at a pace no civilization had ever attempted before, and the engineers tasked with building its infrastructure faced a problem that would have seemed impossible to solve. They needed to construct ports and seawalls in the middle of salt water, structures that would need to hold together against relentless waves, tidal forces, and the corrosive chemistry of the ocean itself. The materials available to them should not have been enough, and yet they built something that time itself could not destroy. The Romans called their mixture opus caementicium, and at first glance it did not look like anything special. It was a combination of volcanic ash, seawater, lime, and chunks of rock, poured and packed into wooden molds along the coastline. The volcanic ash came primarily from a region near Naples called Pozzuoli, and for centuries, historians simply noted this as an interesting detail without fully understanding its significance. But when modern researchers began examining ancient Roman seawalls pulled from the ocean floor, they discovered something that should not have been there. The concrete was not just holding together, it was actively growing stronger, forming new mineral crystals inside its structure that were reinforcing it from within. This discovery was made possible by a team of researchers led by Marie Jackson at the University of California, Berkeley, who used some of the most advanced imaging technology in the world to examine Roman concrete samples at the molecular level. What they found inside those ancient samples was a rare mineral called tobermerite, a platy crystalline structure that grows very slowly within the concrete matrix and acts like a natural reinforcement system. The longer the Roman concrete sat in seawater, the more tobermerite it produced, and the stronger it became. This was not an accident. This was chemistry working in harmony with the environment in a way that took researchers years to fully explain. The volcanic ash from Pozzuoli, known today as pozzolana, was the key ingredient that made the entire reaction possible. When this ash comes into contact with seawater and lime, it triggers a set of chemical reactions that produce a binding mineral gel called calcium aluminum silicate hydrate, which over time transforms into those tobermerite crystals. The Romans did not have chemistry textbooks or electron microscopes. They learned this through centuries of trial and observation, through builders passing knowledge from one generation to the next, through the slow accumulation of craft expertise that modern industrial construction has almost entirely abandoned in favor of speed and standardization. What makes this even more remarkable is how deliberately the Romans sourced their materials. The volcanic ash was transported across significant distances at considerable cost, and Roman engineers insisted on it even when alternatives might have been cheaper or easier to obtain. Records from the period show that pozzolana was treated as a premium construction material, and structures built with it were understood to be fundamentally different in quality from those built without it. The Romans knew that what they were doing worked. They just did not know exactly why it worked, and that distinction turned out to matter enormously when their empire eventually collapsed and their building traditions were lost. After the fall of Rome, European construction slowly shifted toward different techniques and materials. The precise knowledge of how to combine volcanic ash with lime and seawater in exactly the right proportions was not written down in any single comprehensive document that survived the medieval period. Builders moved toward fired brick, cut stone, and eventually toward a precursor of Portland cement, which was developed in England in the 19th century. Portland cement became the foundation of modern construction, and it transformed the world. Bridges, skyscrapers, dams, and highways rose in quantities that would have stunned even the most ambitious Roman engineer. But Portland cement came with a hidden flaw that nobody fully appreciated until the infrastructure built with it began to age. Modern Portland cement concrete is extraordinarily strong when it is first poured, but it is chemically unstable over long periods of time. It reacts poorly with seawater. It cracks under the expansion and contraction caused by temperature changes, and it does not have any self-reinforcing mechanism built into its chemistry. Engineers compensate for this by embedding steel reinforcement bars, called rebar, inside the concrete. But saltwater corrodes steel, and when the rebar rusts, it expands and causes the concrete around it to crack and spall. The infrastructure crisis that many cities and countries are currently facing, with aging bridges and seawalls requiring constant expensive maintenance, is in large part a consequence of this fundamental chemical limitation. The Roman seawalls at Caesarea Maritima in Israel, built over 2,000 years ago by King Herod using Roman engineering techniques, still exist beneath the waves of the Mediterranean in recognizable condition. The ancient harbor structures at Cosa on the Italian coast have been studied extensively and show virtually no degradation from their original construction. By contrast, the concrete seawall at the Port of Los Angeles, built in the 20th century, began showing significant deterioration within decades of its construction. The comparison is not just interesting. It is a practical engineering challenge with enormous economic consequences, because coastal infrastructure is among the most expensive and critical in the world. What the Roman formula offers is not just historical curiosity. Researchers at the Berkeley lab and at universities across Europe and the United States have been working to reconstruct a modern version of Roman concrete that could be used for marine construction projects. The challenge has been that Pozzuoli in its original form is not available everywhere, and scaling up production of a material that takes centuries to fully cure is not compatible with modern construction timelines. But scientists have identified volcanic ash deposits in other parts of the world with similar chemical properties, and they have developed accelerated testing methods to verify that the same tobermerite-forming reactions can be triggered in these alternative materials. In 2023, a team published findings in the journal American Mineralogist that outlined a viable pathway toward producing Roman-inspired concrete using locally sourced volcanic materials from various regions around the world. The implications for coastal construction, for seawalls, for underwater foundations and harbor infrastructure are significant enough that multiple government agencies and construction firms have expressed interest in funding further development. The idea that ancient knowledge could solve a modern infrastructure crisis has a certain resonance that goes beyond the purely technical. But the excitement around this research is grounded in real engineering potential. There is also a sustainability dimension to this story that is worth understanding clearly. The production of Portland cement is one of the most carbon-intensive industrial processes on the planet, responsible for approximately 8% of global carbon dioxide emissions every year. The high-temperature kilns required to produce Portland cement clinker consume enormous amounts of fossil fuel energy, and the chemical process itself releases carbon dioxide as limestone is converted to lime. Roman concrete, by contrast, is produced at much lower temperatures and relies on volcanic ash that requires no high-temperature processing at all. A shift toward Roman-inspired concrete formulas for marine applications could meaningfully reduce the carbon footprint of construction in exactly the environments where Portland cement performs worst. The story of Roman concrete is also a story about the relationship between knowledge and civilization. The Romans did not invent Pozzuoli concrete all at once. It emerged from centuries of experimentation by builders working in volcanic regions of Italy who noticed that certain local materials produced unusually durable results when mixed with lime and water. This knowledge was refined over generations, institutionalized by Roman engineering corps, and deployed at a scale that matched Rome's imperial ambitions. When the institutional framework that supported that knowledge collapsed, the knowledge itself began to erode, not immediately, but gradually, as the master builders who carried it in their memories and hands aged and died without fully transmitting what they knew. This is a pattern that appears repeatedly in the history of technology. The knowledge of how to produce Damascus steel, the incredibly hard and flexible metal used in medieval Middle Eastern sword-making, was lost when the trade routes that supplied the specific ore used in its production were disrupted. The techniques for producing certain medieval stained glass colors were lost when the workshops that made them closed. In each case, the knowledge existed not as written documentation, but as embodied craft practice. And when the social and economic conditions that sustained that practice disappeared, the knowledge went with them. Roman concrete is unusual because the physical evidence of what was lost survived in the sea walls and harbor structures the Romans left behind, giving modern researchers something concrete, in every sense, to study and learn from. What scientists have recovered from those ancient structures is not just a formula for a building material. It is a reminder that human knowledge is not always cumulative, that progress is not always linear, and that the solutions to modern problems sometimes lie buried in the past, waiting to be rediscovered. The Roman engineers who mixed volcanic ash with seawater along the Italian coast 2,000 years ago were solving a problem. One wave, one storm, one century at a time. And the structures they built have outlasted everything that came after them. That is not just impressive. That is a lesson worth paying attention to. Support by clicking the subscribe, put on the notification bell button for more exclusive content like this. See you on the next one.